we covered a little bit about gases molecules when we visited the molecular kinetic theory. In chapter 3, when we discussed matter, we said matter exists in 3 physical states: gas, solid, and liquid. And we described the differences between them. And let me review what we talked about when it comes to gases. Gases usually are tiny molecules. They move around randomly and independently, meaning they don't need to push each other. Rather, they are so tiny that they could move very freely. And the attraction between those molecules are usually very small. And that is the reason why when you fill up a tank or a cylinder with an amount of gas that it doesn't fill up more than half of this tank, it goes and fills up the entire space in the cylinder. And the entire space of the cylinder is getting filled with an amount of gas that shouldn't actually fill up more than half of the cylinder. That is due to the reason of those molecules being attracted very weakly to each other. And a very simple change, such as temperature. If temperature gets increased, those molecules will be moving faster, and because they're going to be moving faster, they're going to collide even more. And when they collide even more, that causes the increase in pressure. So that's just an example of one of the changes that gaseous compounds go through and the outcome of that effect. So the kinetic molecular theory, once again, describes the gaseous molecules as basically tiny molecules where they move very randomly and independently. And when they move around, they basically collide with each other. And there is a very weak attractions between them, and that's the cause behind why they fill up the maximum amount of space possible for them due to that weak attraction. And as we said, increasing temperature will always increase the collision of those molecules, and therefore increases the pressure. So that's the kinetic molecular theory that usually we relied on to understand the behavior of gaseous molecules. Gas pressure, it's one of the properties that we gonna be studying in this chapter. So, and you see the rest of the properties here actually. So pressure, which is the symbol P, volume, symbol V, temperature, symbol T, and you have the number of gas particles, which are usually expressed in moles, and that's the symbol of N. Okay, so we're gonna learn later on gas laws where you're gonna be relating those with each other. So you may be relating P to V, or P to L to T, or V to T, or P to N, or all of them together. So we're going to learn all of these gas laws, which I will make those gas laws made available to you on an exam handout. And in fact, that exam handout, I will actually publish it immediately, so that way you could start using it for the purpose of the homework or the quiz. So the pressure, it's a property that results from collision of molecules with each other and with the wall of the container. So when you have basically molecules colliding with each other, that will actually be the main cause behind the pressure amount, or the pressure being exerted from the container. Now, in addition to that collision of those molecules with each other, the molecules with the wall of the container can also contribute to the amount of that pressure. There are several units accepted, and all these conversion factors are going to be given to you in the exam handout. So you have 1 atmosphere equals 101.325 kilopascal, which equals 760 millimeter mercury, which equals 760 torr. That's basically what all are basically equivalent amounts. So these are conversion factors. They can go from atmosphere to kilopascal, or kilopascal to millimeter mercury, or millimeter mercury to torr, or torr to atmosphere. All these are basically accepted units. You also have the other one, which is 1 bar equal 100 kilopascal, which equals this much atmosphere, which equals this much millimeter mercury. To eliminate the confusion, I'm not going to give you the second line. I will just give you the first line. So what you're going to see on the exam handout, let me just go ahead and show you that. You're going to have this being shared with you. So exam handout, you could see here useful conversions. 1 atmosphere equals 760 millimeter mercury, which equals 760 torr, which equals 101.325 kilopascal, which equals 14.68 pounds per square inch, PSI. PSI. It's a very important unit because that's the unit that they use in industry. If you look at the tires, if you look at cylinders in hospitals, I mean, there are a lot of tanks that we have measured pressure being monitored. We see it actually in the measured in the unit of PSI. So it's very important that we be aware of what it is, the conversion unit from PSI to atmosphere or any other units. So someone might say, okay, well, you're giving us all these conversion factors. How are you going to ask a question? Well, let's look at the worked example file. So the worked example file, I have a question that's on slide number 3, sample problem 8.2. The oxygen in a tank in the hospital respiratory unit has a pressure of 4,820 millimeter mercury. Calculate the pressure in atmospheres. Okay, so that's a simple unit conversion. So you are given 4,820 millimeter mercury, and you are being asked to get it to atmosphere. So you have a conversion factor that is already listed in the exam handout. Says 1 atmosphere equals 760 millimeter mercury. So all what you need to do, start with what's given, 4,820 millimeter mercury, and then you time it by a conversion factor. The conversion factor has to be set in a way that will allow you to cancel out the millimeter mercury. So that's why you need to write 1 atmosphere over 760. You do the math, you know already that you have 3 sig fig, so your final answer should have 3 sig fig. That's how simple it is to ask a question when it comes to unit conversion of the property of pressure. Volume, that's another property that's usually expressed in the unit of liters. Temperature, usually expressed in the unit of Kelvin. And we already know that to calculate the temperature in Kelvin, we add up the Celsius plus 273.15. This is given to you in the exam handout. So if you go to the exam handout, you will find it on the right-hand side listed. So you have the Fahrenheit equals Celsius times 1.88. I don't know if you are able to see this. I hope you are. Okay. So you have the two equations that have to deal with units conversions of temperature. So you have Fahrenheit equals Celsius times 1.88 plus 32, and Kelvin equals Celsius plus 273.15. The temperature, when it comes to gas laws, has to be expressed in Kelvin. So you cannot plug in a value in any of these gas laws unless that value of temperature is in the Kelvin unit. If I'm giving it to you in the question in Fahrenheit, you need to convert it to Kelvin by getting it to Celsius, then to Kelvin. If I'm giving it to you in Celsius, you need to convert it to Kelvin directly using the second equation. And finally, the amount of gas will be in units of mole. So gas laws that we're going to be going over, they are actually, most of them, they have names of those scientists who basically studied those properties very extensively, and they came up with these numerical equations. And if you if you look at the exam handout, you will see that those equations that we're going to be discussing, they're all listed in here. So you could see 1, 2, 3, 4 gas laws. In fact, there's beyond that, there is more, but I will be requiring those basically gas laws to be applied in those questions that you're going to see in the homework, quizzes, or the exam. So let's go over each one by one. So the very first law, which studies basically pressure and volume, which is Boyle's law. Boyle's law. Here's the name of the scientist. Boyle's law. Boyle's law basically studies the relationship between pressure and volume. And this law basically states that the pressure and volume are inversely proportional to each other. What is that supposed to mean? Inversely proportional. That means if volume is decreased, pressure is increased. If volume is increased, pressure is decreased. Think of the can of soda. If you open it, what's going to happen? You're going to hear a sound. Why is that? Because you have a pressure got decreased because of the volume being increased. Because once you open the can, you basically increase the volume where the gas molecules can actually escape and fill up that larger volume. And the reason, and once that volume gets increased, pressure will get decreased. But that law is valid if the other two variables are constant, which is the amount, which is moles, and temperature. So Boyle's law, once again, it states that the pressure and volume are inversely proportional, and it has to be at a constant temperature and amount. So what's the numerical equation of this law? Well, you see it written right here. P1 V1 equals P2 V2. What is 1 and what is 2? Well, 1 and 2 basically refers to the condition before and after. Before the change and after the change. So if I have a certain pressure and a certain volume to start with, and I increase the pressure to a certain amount, so I'm having a change in pressure, that will be P2. What would be V2? So that's how we're going to be basically applying this law. If I have a change in either of the two, pressure or volume, and I'm trying to figure out what happens to the pressure or what happens to the volume, with having the amount and temperature being constant. Let's look at the worked example file. The worked example file has an example where volume and pressure are being related. So if I see the worked example file, sample problem 8.3, it's telling me that when Whitney had her asthma attack, she was given oxygen through a face mask. The gauge on a 12-liter tank of compressed oxygen reads 3,800 millimeter mercury. How many liters would this same gas occupy at a final pressure of 570 millimeter mercury when temperature and amount of gas do not change? This is a typical question where I should think right away of the Boyle's law. Why? Because he's relating volume and pressure, and he's not talking about temperature or amount of gas. So I need to right away label those data as P1, V1, and P2 and V2. Now, P1 and V1, they are basically prior to the change. So this is my V1, 12 liter, and this is my P1, 3,800 millimeter mercury. So you can see them right here. And P2 would be that's 570 millimeter mercury, and he wants the V2. So from the given data in the question, I need to think right away of this equation, which is the P1 V1 equals P2 V2. Plug in what's given and solve what's being asked about. I want to rewrite this equation in a way to solve for V2. What would V2 equal to? P1 V1 divided by P2. This is just a simple math. You solve for V2 since it's the missing variable, and you are basically putting the V2 in one side and rearranging the equation in a way that will allow you to solve for V2. So V2 will equal P1 V1 divided by P2. All right, plug in the given data. So V1 is 12 liter, P1 is 3800, P2 is 570 millimeter mercury. And once you do the math, you know already that you have 2 sig fig times 3 times 2 sig fig divided by 2 sig fig. So your final answer should have 2 sig fig. And the decimal point there, it's a must to show that you have 2 sig fig. Because if you don't have that decimal point, that means you're accepting the answer to be 1 sig fig, which is not correct. So this is a question that could be asked where you will need the Boyle's law to actually be used to plug in the data that's given to you in the question. And once again, you do not need to memorize any of these equations. They are already there in the exam handout. So right there, P1 V1 equals P2 V2. You will need to plug in what's given to you and make sure that you solve for what's missing. Now, keep in mind, the key thing that you have to have the 2 pressure in the same unit, and you have to have the 2 volume in the same unit. So you cannot have one volume in milliliter and the other volume being in liter. You cannot have one pressure being in atmosphere and the other value to be in torr or PSI. You have to unify, and it doesn't matter which one you convert to which, as long as you unify the units. Just keep that in mind. Okay, the second law, which is I want to talk about, is Charles' law. Charles' law, here's the name. Charles' law. And this law basically relates volume and temperature. Volume and temperature. We just said at the beginning when we described the gas's behavior, we said when temperatures increase, molecules move faster, they collide even more, and when they collide, what happens actually, they get farther apart from each other. And when they get farther apart from each other, that's going to cause those molecules to occupy a larger space, a larger volume. Once again, increasing temperature will increase the collision of those molecules. And increasing the collision of those molecules will push these molecules to be farther apart from each other. And when they get farther apart from each other, they occupy a larger space. And that's why the volume is increased when temperature is increased. And this law, in order for it to be valid, amount and pressure have to be constant. What's the numerical equation? Well, numerical equation is the second one. That is V1 over T1 equals V2 over T2. We already said what's 1 and what's 2. 1 is before the change, 2 is after the change. And the relationship that we see in between pressure and volume, they are inversely proportional to each other. One increases, the second decreases. While volume and temperature, they are directly related to each other. What is that supposed to mean? The direct relationship between them means if you increase one, you increase the second. If you decrease one, you decrease the second. That's what it means. So let's take an example on volume and temperature. So here is sample problem 8.4. Calculating volume when temperature changes. Helium gas is used to inflate the abdomen during a surgery. A sample of helium gas has a volume of 5.40 liter and a temperature of 15 Celsius. What is the final volume in liters of the gas after the temperature has been increased to 42 Celsius when the pressure and amount of gas do not change? when I listed the properties at the beginning, and I said pressure, volume, temperature, and amount, I say there that the temperature that being plugged in those gas laws has to be in Kelvin. It cannot be in any other unit. So somebody say, okay, well, he's giving it to me in Celsius. They're going to cancel each other out. Can I just keep it? No, you cannot. You have to convert it to Kelvin. And in order for you to convert it to Kelvin, you need to once again use this equation, which says Celsius plus 273.15. This textbook where these work examples files came from, they ignored the 0.15. I mean, you shouldn't. You should always use the 0.15, but I'm just pointing that out, that this textbook where this worked example file came from, they ignored that 0.15, but your own required textbook is using the 0.15. So we're gonna be applying the same thing in our exams. Make sure that your Celsius gets added to 273.15 to get the Kelvin unit. All right. So what do I have here? Let's label the data as V1, V2, and T1 and T2. V1 being 5.4, T1 is 15 Celsius, so you add it to 273.15, so that will be the 288.15, and T2 will be the 42. You add it to 273.15, so you end up having a value in Kelvin. He wants V2. Okay, so T1, T2, V1, V2. So when you look at the exam handout, you're going to find the only equation that's going to fit this data is the second equation, which is Charles' law. Charles' law is written as V1 over T1 equals V2 over T2. Math taught me that if I want to rearrange this equation to solve for V2, I will need to do the following: cross multiplication, and then solve for V2. So cross multiplication means you have V1, T1 times T2 equals V2 over T2 times T2. Or you could easily just say V2 times T1 equals V1 times T2, and then solving for V2, you will have V1 times T2, V1 times T2 divided by T1. So this final equation right here, it's actually the easiest to get to it by straight from the first one without going through the second. So solving for V2 equals V1 times T2 divided by T1. V1 times T2 divided by T1. We call that cross multiplication. All right, I already have V1, I already have T2, I already have T1. All I need to do is just plug all in, and I already have 3 sig figs all around, so my final answer should be 3 sig figs. That's an example where you are given data that you are basically required to use the Charles' law, V1 over T1 equals V2 over T2. So Boyle's law, once again, Boyle's law deals with pressure and volume being inversely proportional. Charles' law deals with volume and temperature. They are directly proportional. And the third law, which we're going to be talking about now, is Gay-Lussac's law. Gay-Lussac's law relates pressure and temperature. Pressure and temperature. And let me use the same justification that I used for the Charles' law, why the volume is increased when temperature is increased. In Charles' law, we said increasing temperature will increase collision, and those molecules will get farther apart from each other. Therefore, they will occupy a larger space, larger volume. Here, increasing temperature will increase the collision. And we already know collision of molecules with each other will cause increasing the pressure, because that's the main cause behind the pressure, is the collision of the molecules with each other and the molecules with the wall of the container. So that's the relationship. They are directly proportional. Increasing temperature will increase the pressure, decreasing the temperature will decrease the pressure. But this Gay-Lussac's law will be valid only if the amount and volume are constant. Only if the amount and volume are constant. Okay, so somebody might say, okay, well, I don't see it here on the exam handout. Well, if the question, like the one that we're going to go over in the worked example file now, has pressure and has temperature, has no mentioning of volume, well, you have this gas law right here. P1 V1 over T1 equals P2 V2 over T2. You get rid of the V1 and V2. If the question mentions pressure and temperature being related and a change to find the effect of that change and no mentioning of volume, then here's the third equation. You get rid of the V1 and V2, and you just continue on dealing with the Gay-Lussac's numerical equation. Okay, so let's look at that work example file, which is 8.5. Home oxygen tanks can be dangerous if they are heated because they can explode. Suppose an oxygen tank has a pressure of 120 atmosphere at a room temperature of 25 Celsius. So you have pressure and you have temperature. If a fire in the room causes the temperature of the gas inside the oxygen tank to reach 402 Celsius, what is its pressure in atmosphere or atmospheres if the volume and amount of gas do not change? So I have pressure, temperature, and I'm being asked for P2 if T2 takes place. Okay. The very first thing I need to do, I need to get those temperature values that are given to me in Celsius to Kelvin. That's the very first thing I need to do. So get those out of the way. The data that's given to me, pressure and temperature, reminds me of basically using Gay-Lussac's law. I need to get rid of the V1, V2 and V2. So P1 over T1 equals P2 over T2. That will be the result of canceling V1 and V2 of the third equation. Okay, so P1 is given, T1 is given, P2 is missing, T2 is given. So I'm going to solve for P2. P2 equals P1 times T2 divided by T1. So cross multiplication. Solving for P2 equals P1 times T2 divided by T1. Now what do I need to do next? Plug in the values. So P1 is 120, that's 2 sig fig, and you got the Kelvin and Kelvin. So the fact that I have 2 sig figs, I need to have my final answer in 2 sig. Typing the kinetic molecular theory, which talks about the behavior of gases. We talked about the 4 properties: pressure, volume, temperature, and amount, and we highlighted the units that are accepted for each one of those. And after that we went over the some of the gas laws. One of them was Boyle's law, relates pressure and volume at constant temperature and amount, and we said the relationship between pressure and volume is inversely proportional. Increasing pressure will decrease volume, increasing volume will decrease the pressure. We also talked about Charles's law, where it relates volume and temperature, and we said the relationship between the two is direct relationship, where if you increase the temperature, volume will increase. If you decrease the temperature, volume will increase at constant pressure and amount. We also talked about Gay-Lussac's law, which relates pressure and temperature, and we say the increasing the temperature will increase the pressure. So the relationship between the two is direct relationship. And we already seen some of these examples that are in the worked examples file, where we needed to apply those numerical equations of these gas laws to find what's being asked about after plugging in what's required. The key thing in all of these questions that we dealt with, that the temperature has to always be in Kelvin. And other units are accepted for the other properties, pressure, volume, but you always have to keep in mind that V1 and V2, they have to have the same unit. P1 and P2, they have to have the same unit, regardless what that unit is. So let's continue on that. So the next law is Avogadro's law. And we already seen this term, Avogadro, is, a scientist who came up with Avogadro's number. And we said that Avogadro's number is basically refers to how many constituents we have in a mole of substance. And that mole of substance basically contains whatever constituents that will basically equal to 6.02 times 10 to the 23. This same exact scientist came up with a study finding that is a relationship between volume and amount, keeping the temperature and pressure constant, and the relationship is direct, meaning increasing the amount of gas that will basically occupy a larger space, which is volume. So this direct relationship, once again, it indicates that increasing one will increase the second, decreasing one will decrease the second, but the temperature and pressure has to be constant. One of the examples in the worked example file, it's actually, which is example 8.7, it relates to Avogadro's law. So Avogadro's law, once again, it's V1 over N1 equals V2 over N2. Just like the volume and temperature. Volume and temperature are directly related to each other. Same thing, volume and amount. They're also directly related to each other. Okay, so here's a question of whether a balloon with a volume of 44 liters is filled with 2 moles of helium. So I have V1 and I have N1. What is the final volume? So obviously he's asking for V2 if 3.0 moles of helium are added to give a total of 5 moles of helium if the pressure and temperature do not change. So my final amount is 5 moles. So that's the N2. Okay, so applying what I see here in terms of data, once I label them, I have V1, N1, and N2. I am missing V2. So how do I solve for V2? Cross multiplication. So V2 equals V1 times N2 divided by N1. And that's what you see right here. V1 over N1 equals V2 over N2. V2 equals V1 times N2 divided by N1. Plugging in the data, 44, 5, and 2, 2 sig figs all around. So my final answer should be 2 sig figs. And that's what I see here, 110 without a decimal point after the 0 liter. So without a decimal point, that makes the 0 non-significant. Therefore, I have 2 sig figs as a final answer. So that's Avogadro's law. The next law, which is the combined gas law. Let me skip the ideal gas law for a few minutes, and I will come back to it. The combined gas law is basically relating all together. So P1 V1 over N1 T1. So basically you are combining Boyle's law, Charles' law, Avogadro's law, and Gay-Lussac's law. So all these together, you see basically this equation, which is P1 V1 over N1 T1 equals P2 V2 over N2 T2. You're not going to be seeing a question that requires you to deal with all this set of data, but just in case, if you come across a question elsewhere or in the reading material, you know that there is what we call the combined gas law. And it's also, there is another version of this gas law. If you look at the exam handout, the third law, which basically omits the amount. So you could be actually dealing with another version of combined gas law where you would skip the amount and consider only pressure, volume, and temperature before and after. So you could see here P1 V1 over T1 equals P2 V2 over T2. And when you are dealing with an equation like this or the other, you're not going to be dealing with more than one missing variable. So you're not going to be solving for two variables at the same time. You will be given all the other data, missing only one. The key thing, once again, the temperature has to be in Kelvin. Has to be in Kelvin. So let's look at the work example file. There is a question, I believe, deals with, no, I thought I had a question deals with combined gas law. Maybe not. Let's see. Oh yeah, this one. Yeah, this one. So example 4, which is slide number 49, it gives you basically P1 missing P2, gives you T1 and T2. They are given actually in Celsius, so you're gonna have to give them to Kelvin, and it's giving you V1 and V2. This should be V2. I think it's a typo. Yeah, this should say V2. I don't know why it says V1. Okay, so yeah, it's plugged in here as V2. So you could basically use the combined gas law, and you're gonna basically skip the N1, N2. Why? Because there is no mentioning of any amount of gases in this question. So you're dealing with P1 V1 over T1 equals P2 V2 over T2. And that's exactly what you see here, the third equation. And I already taught you in the morning that if you are not given V1 or V2, then you are dealing with P1 over T1 equals P2 over T2, which is Gay-Lussac's law. So it's not mentioned in here, but you could extract it out of this equation. All right. So plugging in the data for P1. So once again, you are solving for P2 here. That's what's missing. So P2 equals P1 V1 T2 divided by T1 V2. So that's a cross multiplication. Once again, solving for the missing variable. And that will allow me to solve for P2 now. Plugging in the data for every single thing that you have will basically deliver the final answer. The final answer has to be 2 sig fig because of the fact that I have 3, 4, 2, 2. So it has to be 2 sig fig at the end. So that's the combined gas law. The next law, which is the ideal gas law. Ideal gas law. So which is PV equal nRT. And you could see here that it relates the 4 properties together, but there's an additional symbol that you're not probably aware of what that is, which is R. We'll get to it in a second. So P is the pressure, V is volume, N is the amount, R is a constant that's given to you actually right there. We'll come to it in a second. T is temperature. Now, when you look at R, which usually is given to you in the exam handout, it's a constant that is 0.08206 or 58. I think I gave it to you as 0.08206 for convenience. And the unit, liter atmosphere divided by Kelvin moles. And because this ideal gas constant already been set when it comes to units, and ignore this value. This is the second value right here. It's something that we use for another equation that is not applied anyways in this course. So totally ignore the second value. Just stick to the first one, 0.08206. Liter atmosphere per Kelvin mole. This tells me the ideal gas constant that the unit of volume has to be in liters, unit of pressure has to be in atmospheres, unit of temperature has to be in Kelvin, and unit of amount has to be in moles. So when I apply PV equal nRT in a question where I'm given data of every single one of them, pressure has to be in liter. If it's not, I have to convert it to liters. Pressure has to be in atmosphere. If it's not in atmosphere, I have to convert it back to atmospheres. Volume has to be in liters. N has to be in moles. T has to be in Kelvin. And R is already given. So if you look at the exam handout, it's right there. Universal gas constant, sometimes referred to as ideal gas constant. You will see it written 0.08206 liter atmosphere per mole Kelvin. So this is something that I don't have to memorize. And here's the ideal gas law right there. PV equals nRT. Let's look at an example. And I believe you should be able to find an example within the PowerPoint slides. So if I have, yeah. So here's a question, a lot of text. How many moles of krypton gas must be added to a 175 milliliter incandescent light bulb to yield a gas pressure of 117 kilopascal at 21.6 Celsius? So this question is different from what we used to deal with previously. Previously, we had initial temperature and final temperature, initial pressure, final pressure, initial volume, final volume. While this question gives you a set of data, single value for volume, single value of temperature, single value for pressure. So that tells you right there that I am dealing with an ideal gas law question. All right. What's the key thing I need to do? The key thing that you need to label the data, that this is volume, this is pressure, and this is temperature, and he's asking for moles. So right away, I need to convert some of this data. So which is the units of kilopascal need to be converted to atmospheres. I mean, I see here that he used the other data, but instead, what I can do is basically get the 117 to atmosphere. And since I already have the exam handout, yep, right there. So 1 atmosphere equal 101.325 kilopascal. So right away, what I can do, I get the 117 converted to atmosphere, and that's the accepted unit for pressure. Again, remember the R constant, the unit of pressure has to be in atmosphere. All right, and the temperature is in Celsius, so I convert it back to Kelvin by adding 273.15. The milliliter has to be converted back to volume in liters, which is going to be 0.175. 0.175. Plug all that in, and that will allow you to get the number of moles, which is going to be 3 sig fig, due to the fact that you have 3 sig fig and a 3 sig fig. So that is the reason why your final answer is written in 3 sig fig. Let's see. Here's another question that deals with the same law. It's giving you amount, but that's in grams. He's giving you pressure, and he's giving you temperature. So he's asking for volume. So once again, I can solve this question in a way that I can use the PV equal nRT. Pressure is already in atmosphere. Volume being asked about. Number of moles, I can get the 1.196 grams to moles by using molar mass. So simply, I can just time the 1.196 divided times 1 mole over how much krypton does weigh. So find the moles of krypton. And then the temperature needs to be converted back to Kelvin. Once I do that, I use the PV equals nRT. PV equals nRT. So solving for volume, then nRT divided by P. nRT divided by P, and that should give me a final answer that is 0.255 liter. So he's using an equation here that's another version of what we actually dealt with, which is a PV equal nRT. We already know that the number of moles is mass over molar mass. Mass over molar mass. And that's what you see here. But this equation, unfortunately, will not be given to you on the exam handout. What's going to be given instead is the PV equal nRT. So if you want to use this equation, you're going to have to extracted from the PV equal nRT, writing N as mass over molar mass. So all what you need to do is basically just plug in the data afterwards. But is it a must to use this equation? No. Once again, you can get this converted to moles. You have the pressure already in atmosphere, get the Celsius to Kelvin, and just simply plug all that in the PV equal nRT, solve for the volume equals nRT divided by P, and that should give you the final answer. So you need to try this question on your own and see if you are able to reproduce this answer. RT number, the R value can be calculated by simply plugging PV divided by NT. Putting the standard conditions which are listed right here in slide number 52. Standard temperature and pressure, STP, and molar volume. And I'm gonna cover the common one. Okay, I'm not gonna talk about the correct. I mean, yes, there's a more correct version of it, but let's just talk about the common one, just for the knowledge part of it. What it is, where does this R come from? The standard conditions usually is 0 Celsius, which is 273.15, 1 atmosphere, for 1 mole for a certain volume. What that volume is 22.414 liter. What does this volume mean? This volume means if I take 1 mole of any gaseous compound and I put the temperature to be 0 Celsius or 273.15 Kelvin, and I set the pressure to be 1 atmosphere, I'm gonna find that this one volume, this 1 mole occupies a volume that is 22.414 liter. That's what we mean by molar volume. And if I plug in that equation, which is PV equals nRT, if I plug in the pressure to be 1 atmosphere, if I plug in the volume to be 22.414 liter, if I plug in the moles to be 1 mole, if I plug in the T to be 273.15 and solve for R, this R will be the value that you see on the exam handout, which is, once again, 0.08206. So this number, which is ideal gas constant, came actually from the molar volume, which is usually measured at STP. So you could be getting a simple question where, which of the following is considered standard temperature and pressure? Well, standard temperature and pressure is condition where we find the molar volume. The standard temperature and pressure is when you have the temperature being 273.15 Kelvin or whatever equivalent to it, such as 0 Celsius, and the pressure to be 1 atmosphere or whatever equivalent to it. So that's what the STP is. Now, since then, I believe 1996, there was another theory came in and said that the more accurate molar volume being found actually when the pressure to be considered 1 bar, not 1 atmosphere. So if you see these two versions, it's just because of the two theories that obviously now the approved theory is the more correct, even though a lot of textbooks still use the top part being the molar volume. So the bottom part basically changing the conditions of what you see here, 273.15 and 1 atmosphere to 273.15 and 1 bar, and that plugging all that in the same equation, which is the PV equal nRT, the molar volume it changes slightly to 22.711 liter. So once again, molar volume means 1 mole of any gaseous compound at STP condition will occupy a space that is the molar volume, which is 22.414 liter, the common value, the more correct value, which is 22.711 liter. Which of the two are you required to know? You're not going to get both of them in the same multiple choice question. You will see one of them. So it depends on that textbook where the question is coming from. You will see one of them being approved. And once again, 1 out of 10 textbooks, you will see the bottom value. 1 out of 10 textbooks. So a lot of textbooks still are sticking to the common way to define STP. So that's basically where the R value came from. Dalton's law. Dalton's law. What is Dalton's law? Dalton's law in brief tells me if I have a container consists of several gaseous compounds, the total pressure of the container will equal to the partial pressure of every single component being added up. Once again, Dalton's law of partial pressure states that the total pressure of a mixture of gases is equal to the sum of the partial pressures of all the gases. And you're only going to be required to know this top part, which is, once again, the P total equals partial pressure of A plus partial pressure of B plus partial pressure of C, or whatever number of gases, compounds in the container. So here's a question where it's an application of this partial pressure or Dalton's law. So you see here that, which is the worked example file, sample problem 8.9. The gas mixture has a total pressure of 700 atmosphere. If the partial pressure of the oxygen in the tank is 1140 millimeter mercury, what is the partial pressure in atmospheres of the helium in the breathing mixture? So obviously, the challenging part here is to recognize that we're dealing with Dalton's law question. The fact that it's talking about total pressure and partial pressure of one and partial pressure of a second, then right away I need to think of the P total equals the partial pressure of A plus partial pressure of B. A being oxygen, B being helium. Okay, so the total is 7 atmosphere. Partial pressure of oxygen is 1140 millimeter mercury. I cannot deal with more than one unit in the question. So I'm going to have to convert them all back to atmosphere. Why? Because the partial pressure of the helium being asked about, he wants it to be in atmosphere. So right away, I know already that I have a conversion factor in the exam handout that relates 1 atmosphere to millimeter mercury, which is right there. Right there. So 1 atmosphere equals 760 millimeter mercury. So that's the very first thing I need to do. Get the millimeter mercury to atmosphere. So that will be 1.50 atmosphere. So 3 sig fig, keep it 3 sig fig. All right. So now I have the partial pressure of oxygen, and he wants the partial pressure of helium. So I know already the P total equals partial pressure of oxygen plus the partial pressure of helium. What would the partial pressure of helium equals to? The total minus partial pressure of oxygen, and that will be 5.50 atmosphere. So it's very, very straightforward application of the Dalton's gas law when it comes to calculations. So there's no really tricks to play with when it comes to this gas law. Okay, and I think this is another question where neon line contains neon gas mixed with argon gas. If the total pressure of the mixture is 1.30 kilopascal and the partial pressure of neon gas is 0.27 kilopascal, what is the partial pressure of the argon gas? So obviously you're going to have to subtract 0.27 from the 1.3, and that will be the value of the argon partial pressure. Just talked about, which is the STP. What is the volume in liters of 64 grams of oxygen gas at STP? So clearly, he's giving me a temperature value, pressure value, an amount value, asking for volume. So that should remind you right away of the ideal gas law. Ideal gas law. So the ideal gas law, which is where you are required to get the grams to moles, and you need to make sure that the temperature and pressure are available. So temperature will be the 1 atmosphere, temperature will be the 273.15 Kelvin, pressure being 1 atmosphere. So you could do the PV equals nRT to solve for this, or you could use the molar volume, which is a conversion factor that tells me 1 mole of anything occupies a volume of 22.4. So once I get the number of moles of the 64 grams, once I get that using the molar mass, right away I can use the molar volume. So from mass, I use molar mass to get the moles, and from moles, I use the molar volume to get the liters. So if this approach is confusing, you could just simply use the PV equals nRT for this question. PV equals nRT. And you should get the same answer, which is 44.8.